So make a note of this. The two methods we've talked about so far, neither of these will work. If I try to use substitution, we talked about this before, this x is not going to disappear if I let u equal sine x or something like that. And also the trigonometric identities we've looked at are to do with sine squared x and converting that to sine x. So neither of these two are going to help in this situation. I've got two functions multiplied together. So x times by the sine of x. And there is a rule that we use which is derived from the product rule in differentiation. And it looks like this. And you've got it on your integration techniques handout. That is the rule that we're going to apply in this situation. So just make a note of it and then I'll talk you through what it means. This is our original integral. Oh, it's going to start playing around at that again, is it? This is our original integral, okay? What I do is I let one bit of this be u and one bit of it be dv. I've got two parts multiplied together, u and dv, so I'm going to let one bit equal u and one bit equal dv. The crucial part is deciding which is which. Once we've got that, what we do is we turn it into this right-hand side here. So what does this mean? It means that the thing I call u is just put here. So that's the u. Well, if I say let x equal u, then that will be x. And this is v. I've got dv. So if I let this be dv, for example, then I'd have to integrate that to get v. So what goes here is the integral of whatever we decide to call dv out of these two. And then we take away the integral of v, which is the bit I've just integrated, times du, which is the differential of the bit I've called u. Sounds a bit wordy, but we'll see how it works by example. And what you hope, this is why we use it, what you hope is that the bit I differentiate, so in other words, the bit I'm calling u, I'm going to differentiate and put that in here. The bit we hope that by differentiating we get rid of one of the variables. So in this case, if I were to let x equal u, at some point I'm going to differentiate that, and if I differentiate x, it's gone, it just becomes 1. So then I'll have an integral that that doesn't involve the x, and then I'm hoping I'm going to be able to do that. And so that's the way it works. Let's try it for this. So what we do is we're going to let this be u, which means that by definition this has got to be dv. So that's the first step, deciding which bit to call u and which bit to call dv. And how you decide is by thinking that, well, which one of these, if I differentiate, will disappear. So let's see. So that means we can now, a bit like we did with the product rule many years ago, we can split our page into two columns, and then we let one side, we write down what u is. So u is equal to x, and then we're going to differentiate that. And on the other side, dv was equal to sine x, wasn't it? Sine x. And I'm going to integrate that. So I've got to do two simple, one differential and one integral. The differential of u is 1. And the integral of this gives us v. So the integral of v is minus cos x.
Should that be x?
Yeah, it should, but we're after these sort of, these should all have like dx underneath and all this, but we don't bother to do it.
Okay.
It just tends to confuse, but yes, you are right, we should really have a by dx in here. But let's not confuse the issue. It's differentiated with respect to whatever this is, really. Okay. Now we've put them into our integration by parts. So our original integral, let's rewrite, it never harms to repeat these things, our integration by parts formula. Integral u dv is going to become uv minus the integral of v du. Yeah? I tend to just stick it in right at the end though.
Oh,
Yeah, but yeah. It never harms to repeat this thing, and as you write it down, say it, because then you remember it. Integral u dv equals uv minus integral v du, but it will be on your formula sheet. So now, what is integral u dv? It's the original integral, x times sine x. Oops. dx. And then we plug in what we found out. What is u? It's x. What is v? It's the integral of this, minus cos x. Forget the c for now. Minus the integral of v, which is minus cos x, times du, which is just 1. And I'm going to integrate with respect to x. So that's that. Write that down and then check you see it as you go along. Notice how I've used brackets because of all these minus signs. You've got to be very careful with the negatives. Right, so now I'm going to try and tidy up and worry about these signs a bit. So what does my original integral look like now? There's my original integral. It's going to equal minus x cos x. That's that first bit. But now if we look at this integral, it's minus outside the integral and minus inside. So it becomes plus the integral of cos x. We don't need the 1 dx. And we now have a standard integral that we can look at our table of standard integrals and do. So now if we look at this final integral, we've replaced, what this rule has allowed me to do is replace this original integral here with a differential that I've done and another integral, but one now that we can do. That's a standard integral. Just the integral of cos x is sine x. So we end up with minus x cos x plus sine x. And that's the answer. But now we've done the integral, add the c. So our final integral of x sine x turns out to be this. What about if I was asked to integrate something like that? I would do exactly what we've just done. I'd let u equal x squared and then I'd run it through. But I wouldn't get rid of x, would I? Because if I differentiate x squared, I'd have 2x. So what do you think I do now? No, I'd end up with 2x times something. So I would do it again. So sometimes you have to use integration by parts more than once. If I've got x squared, I think to myself, that means I've got to use this method twice. If I've got x cubed, I've got to use it 3 times. And each time I'll end up with, eventually rather, I'll end up with one with a standard integral in it that I can do. So it can get quite long-winded. But it works.